Alright class, in today's video we're going to be looking at a couple of different types of motion graphs. The ones we're going to be focusing on our four types. We have what we call ticker tape diagrams, often called particle diagrams or oil drop diagrams. We have position versus time graphs, velocity versus time graphs, and then lastly acceleration versus time graphs. So this video is going to mainly focus on kind of our bottom three types of graphs. We'll look on types of data that we'll be plotting, kind of inferences we can make about an object's motion based upon the information contained within these graphs. So for each graph, what we're going to do is kind of focus on these three big things, and then we're looking at them, when we analyze them, we basically want to know what is going to be at a given moment in time, what our y value of our graph is, what our slope is, and lastly, what our area under the curve might tell us. So for each of these, we can either describe these qualitatively, thinking, is this value positive, is it negative, is it zero? Or we also might do the more quantitative, actually do a numerical calculation for things like slope and area. So for our first type of graph, what we have is our position versus time graphs. Right? Basically what we're doing is positions can be plotted along our y-axis. Time for every single one of these graphs is going to go along our x-axis. So we have kind of our x versus t graphs. So when we're looking at these graphs, right, first thing we want to know is think about what does our y value tell us. So let's say we have a y value of 0. Basically what that's telling us is that our position is going to be equal to 0. So that's anywhere we're along the graph, again along our x-axis. So we have y value 0 here for our position. So basically whatever our position is going to be 0, this means that our object is going to be located at the origin. So if we have something that's moving in the y direction, so up and down, maybe the origin might be at ground level. If we're looking at motion on the x-axis, maybe that just might be whatever our predefined starting point might be. In the case in which we have a positive y value on these position versus time graphs, again, this is looking at any section that's going to be above the x-axis. So we're looking, right, anytime our graphs can be in this region above, basically means that we're going to be located in the positive direction relative to our origin. So sometimes we might refer to this as like the direction moving to the right. Maybe we might have an object that's moving kind of upwards, or we have up and down as that coordinates. Could be thinking of forward, backwards, right? Whatever we're defining as our positive direction when we're above our x-axis. So we're going to be located. Again, this is basically telling us where our object's position is going to be. So we're going to be located in the positive direction relative to the origin. And the flip of this, again, if we have the negative value for our if we have a negative y value here on our position versus time graph, we're looking at a section that's going to be below our x-axis, basically means we're going to be located in the negative direction relative to our origin. So for below our x-axis, we have a negative position, and in the case of our right versus left, which just means that we're located left of the origin. Now, the first thing that we're going to do in terms of an actual calculation on these graphs is then looking at our second thing we have. Right? We want to know basically at some given time what's going to be the slope of this position versus time graph. So on our position versus time graph, the slope is going to give us the velocity of our object. And again, our slope, if it's going to be a value of 0, basically what we're going to have is just a horizontal line, be a slope of 0. Basically what this is telling us is that we have then a velocity that's equal to 0, basically means that our position doesn't change, our object's not moving. So again, we have no position change. Means the object is not going to be in motion. If instead we have a positive velocity, if we have a positive slope, means we have a positive velocity, our object's going to be moving in the positive direction. So this would symbolize our object moving towards the right in this case. And if we have then a negative velocity, right, a downward slope, that negative velocity then just means we're going to be moving towards the left. So moving in our negative direction. So we'll eventually be kind of calculating actual values for these slopes, right, using our y2 minus y1 over x2 minus x1 equation. But if we want to just compare them qualitatively, right, basically what we can say is that if we have a steeper slope, just means our object is going to be moving faster. Right? So we're having a larger change in our position in that same given amount of time. So this is if we have what we call uniform or constant slopes. If we have a graph that is concave up, so again, we can either look like this or like this, right? These both represent concave up curves. Basically what this is going to represent is an object that's going to have a positive acceleration. And with this positive acceleration, there's really two possible ways that this can happen. We could either be speeding up while moving in the positive direction. That's like our curve on the left there. So if we are speeding up while going in the positive direction, that would be a positive acceleration. We can also, though, be slowing down in the negative direction. And we can see that that's going to be our curve that's going to be on the right here, right? Basically what we have is a negative slope, right? So it means we're going in the negative direction, but we'll notice that curve gets less and less steep. So that means we're going to be not going as fast as time continues forward. So we're slowing down, but we're still moving in the negative direction. Will still give us this concave up positive acceleration. If we have a concave down curvature, so that would look something like this, or we could have something like this as our two possible options. That's going to result in us having a negative acceleration. So again, the two possible cases for this, the one that is shown on the left there, what happens is we are moving in the negative direction, but because our line is getting steeper and steeper, it means we're going to be speeding up. So getting faster in the negative direction is one way we can have a negative acceleration. On the concave down curve that's on the right side, right, that one's going to have positive slope, so we're actually going to be moving in the positive direction, but it's getting less and less steep. So in this case, what we're doing is we're slowing down while in the positive direction. And then the last thing, right, we want to think about is, what does the area tell us? If we're looking at a position versus time graph, area actually does not tell us anything useful about our object's motion. So don't worry about area on these position versus time graphs. So now just to look at kind of a couple examples of these position versus time graphs. Right. So this first one, basically what we can do is we can break it up into different sections. So what we have here is, let's say we're looking for 0 seconds up to 2 seconds. Right. Basically what we have is our object is moving from this coordinate of x is equal to 0 to x is equal to -10. Right, so that's kind of describing what's going along with our y-axis. Again, because we are below our x-axis here, right, basically this means is that we are always going to be located in the negative direction. So maybe let's call negative to the left. So any motion, anytime we're down here in these first 2 seconds, we're going to be located to the left of the origin. And one thing we can also say is we notice that we have a negative slope here. So our negative slope basically tells us that we're moving, again, to the left. We have a negative velocity, and we can determine our velocity here by finding our slope. So we think of our coordinates here, right? We're basically going from the point 0, 0, up to the point 2, -10. So our rise over run equation, again, we have our y2 minus our y1 divided by our x2 minus x1. Basically, that's going to give us a slope of -5 meters per second. So moving with a speed of 5 meters per second, going to the left. The next section we have here, again, from 2 seconds up to 5 seconds. Right. Basically, what we can say here is that for that region, right, our slope is going to be 0. So because our slope is equal to 0, means we're not going to be moving. Right, we have this constant position of -10 meters to the left. For our last region, as we then go from 5 seconds up to 7 seconds, again, basically what this is showing is our object is going to be moving from this position of x is equal to -10 so this is 10 meters to the left of our origin, then going to a position of x is equal to +10 meters. So we're now going to be right of our motion. So basically what this means is that we've moved a total distance of 20 meters. Over this time frame. Again, we can say we start to the left of the origin, we end up to the right of the origin. Another thing we can say here is that because we have a positive slope, means that we are going to have a positive velocity. We're moving to the right. And again, we can calculate this velocity. We know at the point on the bottom, that's going to be our coordinates 5, -10. We're then going to end up at the coordinate 7, +10. So to calculate the slope, right, our y2 is going to be +10. We'll subtract from it our initial y value of -10. divided by our x2 of 7 minus x1 of 5. So 10 minus negative 10, that's going to give us a positive 20. We're going to have 2 on our denominator, so that means we're going to have a speed of positive 10 meters per second for that rightward moving velocity. In the case in which we have a graph that is concave up or concave down, right, this first region of our 2 seconds, right, this is our hallmark of what a concave up graph looks like. So one thing we can say with this is that we're going to have an overall positive slope. And because we are concave up, that means we're going to have a positive acceleration. Again, our positive slope means we're going to have a positive velocity. So what a positive velocity and positive acceleration together mean is, right, that case of us, we're going to be speeding up while moving in the positive direction. All right, so as we start at the origin, we start moving towards the right. Again, as we kind of trace ourselves along here, so as we're moving to the right, so those first 1 second, right, we're moving positive direction, but we're doing it pretty slowly. Right? We're not gaining much of our y value here. We're not moving very far up. Maybe we're at, let's call this position of 0.5 meters in 1 second. But then as our slope increases, gets larger and larger and larger for that concave up, what we get is that, right, our slope at this point up here is going to be much larger than our slope here. So because we have a greater slope, right, basically we're covering more ground in that same 1 second time interval, we're going to be getting faster as we go along. Next up, from our 2 seconds to about 4 seconds here, right, another case in which we have a slope of 0. So that means we have a velocity of 0. So we're not moving, we're staying at the 4 meters. And then for our last region, again, this is going to be our concave down region. So concave down means we're going to have a negative acceleration. And we also are going to have a negative slope here. So our negative slope means that we're going to be moving with this negative velocity, right? We're going backwards, back to the left towards the origin. So from this, right, if we have a negative acceleration, negative velocity, right, basically what happens is we start off with a rather steep slope here. So we're going pretty fast in terms of our speed. We're going pretty gradual in terms of our slope at the beginning. So we have a pretty slow speed. And then when we get to the end, we then have a much steeper slope. So our speed increases here. So what's happening in this case is that we are going to be moving faster and moving in that negative direction. So we'll call that our speeding up in the negative direction. Which again is one of our 2 possibilities of having a negative acceleration. We can either speed up in that negative direction, or we could slow down in the positive direction. But again, this graph's showing us going faster while moving in our negative direction. Our second type of graph here is going to be our velocity versus time graphs. again, with our velocity versus time graphs, again, time is always going to be along our x-axis. So our velocity is going to be along our y-axis. So you have these v versus t graphs. Again, thinking about the meaning of our y value. Right, if we have a y value 0, we're along our x-axis. Right, basically what this is showing us is we have a velocity that's equal to 0. And if our velocity is equal to 0, basically means that we're not moving. So whereas the slope is 0, represent we're not moving, now it's our y values showing we're not moving. If our y value is positive, right, again, we're above the x-axis, just means that we're moving in the positive direction. So positive velocity means we're moving in the positive direction. And then lastly, if we have a negative value, right, for our velocity, again, just means we're going to be moving in the negative direction. So on a velocity versus time graph, if we're looking at the slope tells us something we refer to as our acceleration, right, basically giving us our rate of change of how quickly that velocity is changing. So again, if we have a slope of 0, slope of 0 just means that we have no acceleration. We're going to be moving at a constant velocity. If we have a slope that's positive, just means we have a positive acceleration. If we have a slope of negative, it means we have a negative acceleration. And what we can say is this case, right, the steeper the line is, right, the greater the slope, means we're going to have a larger magnitude in terms of our acceleration. So we're having a much greater change in our velocity over a given amount of time. And then the last thing is if we have what we call a nonlinear slope, right? So again, we either have that concave up or you might have a concave down graph. Either one, basically what this is just doing is representing what we refer to as a non-constant acceleration. And it's in these cases of a non-constant acceleration, that's when we're going to have to use the calculus to describe what's going on here, which again, we'll look at that more during the actual school year. So last thing, again, if we are looking at these velocity versus time graphs, now if we're thinking about the area is going to tell us the object's change in our position. So our change in our position, right, this is sometimes what we refer to as the displacement of our object. And basically what we have is a section of the graph in which our area is above the x-axis. Right, basically just means that we're moving in the positive direction. And if we have an area that's below the x-axis, it just means that our object has then moved in a negative direction. And again, we're looking at these areas, we're always looking over some sort of time interval. So if we're looking at, breaking apart these different graphs, so for our first 2 seconds here, we have slope is 0. So it basically means that we have a constant velocity that's going to be positive. So for those first 2 seconds, we're moving at a constant velocity of 5 meters per second. Again, we're going to be moving forward from the origin in this case. For our next section here, what we have is a case in which our velocity is still positive. We're above our x-axis, but we're going to have a negative slope. So our negative slope means we're going to then have a negative acceleration. So if we have negative acceleration, but we're moving in the forward directions, basically what this means is that we are going to be slowing down while moving to the right. So moving in our positive directions. And again, we could calculate the actual size of the acceleration by using our slope equation. For our next region here, again, basically we're going to be along our x-axis. We have y value of 0. So our velocity is going to be 0 in this case. Basically means that we're not moving. So both this section and our one in red there, they're both showing cases in which we have a slope of 0, so no acceleration. Or no acceleration in the red case meant we were still moving at that 5 meters per second speed, whereas our slope is 0, but we're along now the x-axis. Means we have both an acceleration of 0, so it's constant, but we have a constant speed of 0, so we're not moving. And then our last section here, again, we're going to be below the x-axis, so we have a negative velocity. We also are going to have a negative slope, which means we have a negative acceleration. So those two together, our negative acceleration, but we're moving in the negative direction, means we're speeding up. Our velocity is going from 0 up to -5, up to -10. So we're going to be speeding up while moving in the negative direction. If we then look at our last velocity versus time graph, again, here basically what we're showing is that we have a acceleration, we have velocity that's becoming positive, We're eventually making our way from 0 meters per second up to 10 meters per second over the course of these 7 seconds. And what we can see is that the slope along our graph, at each of these different points, our slope is getting larger and larger and larger with this concave up. So we know our velocity is increasing from our positive slope. But we also know that those slopes are themselves getting larger and larger. So our velocity is increasing, and we can say it's going to be increasing at an incrementally faster rate. And again, from this one, we won't really do too much analysis on this, Again, this really will require us to apply some calculus knowledge to actually better describe what's going on here, which again, we'll cover that little bit later in the school year. For our last graph here, again, we have acceleration versus time graphs. Acceleration is going to be along our y-axis. Time is going to be along our x-axis. So these A versus T graphs. Again, when our y value is 0, we'll have an acceleration 0. Basically just means that we're moving at that constant speed. If we have a positive value, right, our positive acceleration, again, in those two cases, we can either be speeding up in the positive direction or we can be slowing down the negative direction. If we have a negative y value, again, we can either, with our negative acceleration, be speeding up in the negative direction or we can be slowing down in the positive direction. If we look at the slope of our acceleration versus time graphs, slope technically tells us something we call the jerk. We really won't worry about this at all. Not super physically significant for us. It's basically just showing us the rate at which our acceleration is changing. But again, if our slope on this acceleration versus graph is 0, basically what this is just showing us is that we have a constant acceleration. So anytime we have a constant acceleration, this is when we can use our kinematic equations. If we have a slope that's either positive or negative, or even, let's say, concave up, concave down, basically what this is showing us is that we're going to then have a non-constant acceleration. Anytime we have a non-constant acceleration, the only way we can analyze these scenarios is by using calculus. Last thing, again, we're thinking about the meaning of area. Right, our area tells us our change in our velocity. So it's not necessarily the velocity at a given moment in time, but it's how much our velocity changes. So this is going to give us our basic value for delta V. Again, if we did say maybe no information about our starting velocity, we could use our starting velocity and our change in velocity to actually figure out the final velocity at that time interval once it's over. But really just tells us, though, the actual equation we can use to calculate area gives us a change. So if we have an area above the x-axis, it basically means we have a positive change in our velocity. So maybe we're going from a speed of 2 meters per second up to 5 meters per second. Maybe we're going from negative 3 meters per second up to negative 1 meters per second, or anything representing a positive velocity change. Again, for them below the x-axis just means we're going to have a negative velocity change. So looking at our graph here, again, one thing we can do is the very beginning. Look at this first region from 0 seconds up to 2 seconds. Right, basically we're showing an acceleration of 0. So that means we're going to have a constant velocity. We then jump up from 2 seconds to 4 seconds. So we're going to have an acceleration that's equal to 2 meters per second. Sorry, 2 meters per second squared. And basically what we would need from this portion is we would have to know something about our initial velocity at that point to actually determine, are we speeding up while going forward? Are we slowing down while going backwards? I really don't know, but we do know there's going to be an overall positive acceleration. Our last region here, right, what this is doing is this showing that we're going to have some sort of non-constant acceleration. So over this interval, right, acceleration's decreasing from 2 meters per second squared down to 0. So if we were to try to figure out the change in our velocity from a time of 0 seconds up to 7 seconds, right, basically what we need to do to find our change in velocity is we need to look at the area under this graph. So we have no area from 0 up to 2 seconds. From 2 seconds up to 4 seconds, right, we basically have a region from a graph that we can split into a rectangle. So this actually works out to be a square. So we have a base of 2 and a height of 2. So length times width, right, that very first area we have is going to give us an area of 4. And then next up, again, we're going to have a triangle here from 4 seconds up to 7 seconds. So that triangle is going to have a base of 2 and a height, or sorry, a base of 3 and a height of 2. So our second area, we can just use our 1/2 times base times height. So 1/2 times 3 times our height of 2 gives us an overall area of 3. So in total, we can say that our velocity is going to change by a positive 7 meters per second over those 7 seconds time interval. Again, we get that by just adding the area of the rectangle to the area of the triangle.